Welcome to this training on AI fabric design thinking. Today, we will clarify the critical distinction between scale-up and scale-out architectures in AI systems and how they work together to power massive generative AI workloads. Design an AI fabric, you must first accept that modern AI is fundamentally a distributed computing problem. With large language models growing 10x every year, a single GPU simply cannot hold the necessary data or compute fast enough. Therefore, we must distribute the workload. We tackle this using two distinct architectural strategies. First, we have scale-up, which focuses on maximizing the power of a single server node. Second, have scale-out, which connects those nodes to form a massive cluster. Understanding the specific network requirements of each path is the first step in AI fabric design. This flowchart visualizes the decision path. We start with the AI workload demand. Once it hits the single GPU limit, we must split the strategy. The left path, scale-up, happens inside the node using technologies like NVLink. The right path, scale-out, happens between nodes using fabrics like InfiniBand or Spectrum-X Ethernet. Both paths are required for a complete solution. Zoom in on scale-up. Think of this as building a supernode. We connect multiple GPUs, typically 8 in an HGX system, or up to 72 in a GB200 NVL72 rack using NVIDIA NVLink. This is not standard networking, it is a memory semantic fabric. NVLink provides incredibly high bandwidth up to 1.8 terabytes per second per GPU, which is 14 times faster than PCIe. Allows all GPUs in the domain to share memory and work on a single problem as if they were one giant chip, which is crucial for handling the massive memory footprint of trillion parameter models. Here we see the scale-up architecture. Multiple GPUs, GPU 1 through GPU 6 here, connect directly to a central NV switch. This creates a high-bandwidth NVLink domain. Unlike a standard network, this allows every GPU to access the memory of every other GPU instantly, creating a unified compute resource. So you have your supernodes, you need to connect them. This is scale-out. Here, we use high-performance networks like NVIDIA Quantum InfiniBand or Spectrum-X Ethernet. The goal is to connect hundreds or thousands of nodes to tackle jobs that are too big even for a supernode. A key design principle here is rail optimization. In this topology, specific NICs from different nodes are connected to the same leaf switch, being dedicated lanes for communication. This optimizes the network for specific AI traffic patterns like all reduce, ensuring that the massive traffic from one GPU rail doesn't block another. This diagram illustrates a rail-optimized scale-out topology. Notice how GPU 1 in node connects via NIC 1 to switch 1, and GPU 1 in node B also connects to switch 1. They share a rail. Meanwhile, the GPU 2s connect to a completely separate network via switch 2. This parallel structure maximizes bandwidth and minimizes collisions. Finally, we bring these concepts together into the AI factory. In this unified architecture, scale-up and scale-out work in concert. The NVIDIA Collective Communications Library, or NCCL, is the software glue that makes this happen. NCCL automatically detects the topology, using NVLink for fast local transfers and the InfiniBand or Ethernet fabric for internode communication. Hierarchical design ensures that whether data is moving millimeters between chips or meters between racks, it is doing so at the highest possible speed with the lowest latency, defining the performance of the modern data center. Here's the complete picture. Inside Node 1 and Node 2, GPUs communicate via the green scale-up NVLink paths, forming powerful local units. These nodes are then bridged by the thick scale-out path using InfiniBand or Ethernet. This hierarchical approach allows the system to scale linearly, turning thousands of GPUs into a single computing engine.